Good morning, everybody, and welcome to this breakfast seminar titled Sustainable Chemistry from Catalysis to Materials. Today we hear from selected research projects from the Mistra SafeChem project. We'll hear from Jan-Arne Bäckvall, Clara Pirou, and Adam Slaban, who will give updates on their research within the program. Before the presentation starts, just tell you a bit about Mistra SafeChem. This is a 4+4 year research program where we have put together experts from material science, organic chemistry, toxicology, hazard prediction, and life cycle analysis to be able to take a holistic approach to chemical development. The aim is by working on new tools for synthesis and hazard prediction, life cycle analysis, we could mitigate and find risk already in the design phase of development of a chemical or manufacturing process. So by this, we hope to be able to create a better possibility for sustainability by design. The partners we have in the program are, as you can see, the industry partners. And for the sharp eye, one with sharp eye can see that we have the full value chain for manufacture of chemicals, from the producers to the makers of consumer goods and also the one taking care of the waste. So we hope to be able to follow the chemicals throughout the life cycle. There are 6 universities and institutes doing the research, and the main financer is Mistra, but also the partners are contributing to the budget of the program. For more information on the program, you can go to our webpage, mistrasafechem.com. or .se and contact us if you have any more, if you want to know more about the program. And just the overall vision of the program and what to strive for is to enable and promote the expansion of a safe, sustainable, and green chemical industry in Sweden. The breakfast seminar of today is one of the work packages within the program, work package 4. And today we'll hear about the catalysis and materials. And the first speaker is Jan-Arne Bäckvall, professor at Stockholm University, who will tell about his group's work on heterogeneous catalysis. Please, Jan-Arne.
So, as we heard, I will give a lecture about crystalline cellulose as carrier sustainable catalytic organic reactions. And here is the structure of my lecture: palladium catalyzed, oxidative, carbocyclization, and cascade. Then we talk about cellulose as carrier in heterogeneous catalysis. And finally, we give some examples on carbocyclizations with nanometals on crystalline cellulose. Now, catalytic green transformations. Nature's way of carrying out organic transformation is often green. And we have mild reaction conditions, and we have very few side products which are not harmful, and often the reactions are anti-selective. So we have worked with biomimetic catalysis in 2 areas. First area, oxidation via low energy electron transfer, and these oxidations can often be carried out under aerobic conditions. The second area are cascade reactions, and in many cases involving enzymes. So the combination there with enzymes and metals leads to dynamic kinetic resolution. So we have worked with homogeneous, heterogeneous, and enzyme catalysis. And in these reactions, we are using homogeneous metals and also heterogeneous. This is a nanometal, it's an electron microscopy of palladium 0, and then also enzymes. But today I don't have time to talk about the enzymes. I will only talk about the metal catalyzed reactions. Okay, oxidative carbocyclization of enalenes. Enalenes are very special because they are nucleophilic in the middle position. So when a transition metal coordinates like this, you will activate the allylic CH bond, and you have a CH bond cleavage. And then the middle carbon in the allene attacks the palladium, and you get this intermediate. And this is followed by an olefin insertion to get an intermediate that can undergo a beta hydride elimination. And in this reaction, you get palladium 0 that is reoxidized by benzoquinone back into the cycle. Now we have used, I have an example here of a cascade reactions where we use this first sequence. You see this compound leads to this pyrroline intermediate, the same as here when X is nitrogen. But in this reaction, we also include maleiamide as shown here. And this maleiamide can trap this intermediate, so we never isolate it, but it continuously going on, and we get this, after a cycle addition, we get this more complex structure. And as you can see here, we start from a linear compound, and in the end we get an advanced complex structure where we have 3 rings. So this is, and these products are of course interesting from a biological activity point of view, and they are interesting for pharmaceutical industry. Now, nanopalladium catalysis, we have this, we are using a mesocellular foam material, which is a silica material, and here you have small cavities which are spherical, connected to each other, and this silica material contains a lot of hydroxy groups. And this 3-aminopropyl trimethoxysilane, which is a 3-carbon unit here with an amine, there you bind this silica to the hydroxy group of the siliceous material, and there you have the amine as a binding site for metals. So we add palladium 2 here, and the palladium 2 is binding nicely to the amino group. It's a very strong bond actually between the amines and palladium 2. And then subsequently we reduce it with sodium borohydride to get these nanoparticles as shown here. And this is our nanopalladium catalyst. It's active nanoparticles of palladium. And this is the electron microscopy of these nanoparticles. As you can see, you have small dots here. This is the nanopalladium, and this is the scale bar, 10 nanometers. So these particles are between 1 and 2 nanometers. And interestingly, you can also see the sphere of this in the material. It should be about 26 nanometers, as was shown on last slide. So that is an interesting bonus of this electron microscopy spectrum that we have here. And this is what you had on the slide before. You bind this 3-carbon silica with an amine, and you bind palladium 2 and you reduce it. And these nanoparticles are efficient catalysts for carbocyclization. And this, in this case, we use this enalenol, and you use a double carbonylation, so you have 2 carbon monoxide being included in the product, and you get these interesting lactones. This reaction can be recycled 9 times without any change in yield. The palladium leaching is actually less than 0.1 ppm, which is excellent because there is you cannot detect any leaching of palladium. And you can also use this reaction for the corresponding amines, as shown here, and then you get lactams. And lactams are important in pharmaceutical industry. Now I will talk about this crystalline cellulose as carrier for catalysts. And here we have crystalline nanocellulose. And as you can see, as you know, we have a lot of hydroxy group in cellulose. So we use this hydroxy group exactly in the same way as we use the hydroxy group in silica. And we can bind now these 3-carbon silyl units to the hydroxy groups. And here we have also bound the metal to the amine, which was here before in this 3-carbon silica. And then we get an active nanometal catalyst, where we can use simple starting material, for example, unsaturated hydrocarbon, and transform them into functionalized organic compounds such as lactone, lactams, and other heterocycles of interest for pharmaceutical industry. So here we are using a heterogeneous palladium catalyst, and the idea was to start with these allenes, aminoallenes, and activate this allene exactly as I discussed on the first slide, where we had palladium now activated to form this dienyl. And now the question is, can we introduce CO here and make this pyrrolidones, this kind of lactams? And SCNC is as crystalline nanocellulose, so we have this as carrier now for palladium. And indeed, this reaction was tested. And look here, interestingly, we found that when we run it under normal conditions, we got nothing, 0% yield. And when we added just 1 mole% of silver, we got a 93% yield of this desired product. So the question is, what is silver doing here when it has this effect in this very small amount? So it's a dramatic effect by the silver. So the role of silver, we believe, is that it strips off the chlorides on the catalyst. So we have measured the ratio chloride to palladium before adding additional silver. It's about 2 here. And then after additional silver, it's almost 0, this ratio. And also interesting, we can see that the XPS changes a little bit. The red is after additional silver, and the black is before additional silver. And we believe that what is happening is the following, that these chloride are now, we know that the silver chloride form very strong bonds and fall out as a precipitate, and we get this cationic catalyst, which is the active catalyst. And now don't look too much on this structure if you're not an organic chemist. We usually put them on just to show that we can make many compounds. Who are not an organic chemist can look only on the first row here and maybe on the first example or something. And so we are using this now in a loading of 0.5 mole%, and we can get high yields of these interesting lactams or pyrrolidones. And the reaction can be recycled 9 times here, and you see the ninth time we have still a yield above 90%, so it's very efficient. And the XPS here shows that after the first run and 9th run, it's the same. So the red and black here are the 2 after the first and 9 runs. So nothing is happening here. And also the TEM, the electron microscopy after the first run and the 9th run as shown here. And as you can see, they are identical almost. So you cannot see a difference. You have the same particle size. Now, in this MISTRA SafeShim, one goal was to use first row metals, because previously we had used palladium successfully. Of course, you can argue that palladium also, when it is not leaching, can be very interesting, and one should not only look at the metal, but it's of course it's much easier if you can change to first row metals, and that is one of the goals. And here we have changed to nanocopper. We mobilized the microcrystalline cellulose. So here we have the same aminopropyl unit. It's immobilized on microcrystalline cellulose, and microcrystalline cellulose is shown here. Has a very low price. It's abundantly available. It's has a high surface area, and important, it's biodegradable, of course. And this was also applied to the previous case. Now we bind copper 2 as we've done before with palladium 2, and then we reduce with sodium borohydride. But in this case, you get the mixture between copper 1 and copper 2. And that is the nanocopper catalyst, and the particle size is about 3 to 8 nanometers. and the ratio between copper 1 and copper 2 is 1.1 to 1. And this catalyst here, the nanocopper catalyst, is actually a very dark blue powder. It looks almost black here, and in reality it's really dark blue. So it's anyway, this is a powder that you can just charge into the reaction and run, so it's very easy to handle. Now here is the nanocopper immobilized on MCC, and it is the TEM that we STEM, the scanning transmission electron microscopy, and we can see from this we conclude that the particle size is by analysis 3 to 8 nanometers. The reaction, the nanocopper was used in a carbocyclization of alanine-amides, and you see we run this is a this alanine cyclizes into this important pyrroline. And this work was done in together with Magnus Johansson at AstraZeneca. So it's a work between industry and the Stockholm University. And again, just put a lot of structures here. You have only to look on the first line, maybe one of the first 3 cases to see the yields and so on. This is an efficient catalyst that can be recycled many times. And you can see here after the sixth time, the yield is still very high. And the leaching of copper is less than 1 ppm. So it's a robust and useful catalyst. Now to the mechanism on this nanocopper catalyst carbocyclization. We have considered 2 mechanisms. The upper is following the same pattern as the palladium, where we have a CH activation and form a dianyl copper dicyclysis. But look here, you have only to look on this vinyl copper. This is crucial for the mechanism. Now, if it's hydrolyzed, you will get this proton in this position. However, if you have the lower mechanism, which is an alderine reaction, this hydrogen that ends up here in the vinyl comes actually from the molecule in an intramolecular reaction. So by deuterium labeling, where we put deuterium in these positions of the alene and run the reaction, we found that 100% of the deuterium actually came from the molecule, because we have protons in the solution now, so we can just rule out the above mechanism. So it's actually the lower mechanism here that operates. Our conclusions: crystalline cellulose was used as carrier for metal catalysts, and we have used heterogeneous nanopalladium for oxidative carbocyclization, and the nanocopper was used also for carbocyclizations. And here is a group picture that was taken last summer. Now, the 2 people that have been involved in MISTRA SafeChem is Chiao Cheng here, and here we have Daniels Postivins, and now both of them have left the group, so they are replaced by Dr. Haibo Wu now, who is in the MISTRA SafeChem. And here we have the financial support. The ERC was used in the earlier part of these projects before the MISTRA SafeChem. So, and here is MISTRA SafeChem, and I finally would like to thank you for your attention.
Great, then I will go ahead. So thank you for the introduction, Rickard. As mentioned, my name is Clara Piero, and I'm responsible for the materials development team at RenFuel. My apologies, in the beginning here of the presentation, I just got back from COVID, so my voice might be a bit weak sometimes, but I think it will be fine. So the topic of my presentation today is lignin from wood residue to bioproducts. So the aim of my presentation is to talk a bit about RenFuel as a company and our technology, but I will also talk a bit about the role of RenFuel in Mistra SafeChem and what type of plans we see ahead from here. So with that said, I'm just going to go ahead and tell you a bit about RenFuel in brief. So RenFuel is a leading developer and producer of bioproducts made from lignin. And I usually like to stop there for a second just to tell everyone what lignin is, because that's not necessarily something that everyone is entirely aware of. So lignin is a raw material considered a residual product from the pulp and paper industry. And if you like to visualize what lignin is, if you look at a tree, for example, I usually describe it as the cellulose is like the skeleton of the tree. It makes up about 45% of the tree, while the lignin is more like the glue holding the structure together, and up to about 1/3 of a tree is made out of lignin. And this raw material is actually the base for all our innovations at RenFuel. And with that as a base, we have so far invested 250 million SEK in research, development and production based on lignin-based innovations. So I will talk a bit more about that very soon. We work very actively with patents at RenFuel. So far, our patent portfolio consists of 17 patent families, and we have 60 granted patents to date. So we work very actively within this area. We have a colleague that is responsible of overseeing the patent portfolio, and all colleagues that are within R&D at RenFuel are actually actively working to expand our patent portfolio continuously. Here we look at patent opportunities for the modification of the raw material itself, but also for specific application when it comes to the use of our innovations. So if you're interested to know a bit more about our patents, I added like a note here in teeny tiny text if you would like to look at specific patents or examples of patents that we have. But RenFuel as a company is a startup. We are 20 full-time employees with a wide range of different experiences, but we have an expertise in organic chemistry. Our facilities are in Stockholm, where we have our headquarters, in Uppsala, where we have the R&D site, and we have a 600-liter pilot in Örnsköldsvik. And now I'm going to go ahead and talk a little bit about the products under development at RenFuel, maybe the more fun part. So to the left, you can see a description of biofuels at RenFuel. And this is, in fact, the area we have been working within the longest. So within this area, what we do is that we take lignin from the forest industry and we modify it. So we turn the lignin into a lignin oil. And this lignin oil has a trademark name. It's called lignol. And you can refine lignol into gasoline, diesel, or jet fuel. And this is intended as a drop-in product because we're looking at the market that is driven by regulations. So in Sweden, for example, we have the reduction quota, reduktionsplikten in Swedish. And on EU level, we have the Renewable Energy Directive too. So within the biofuels area, we're currently in a commercialization phase. We're looking to scale up to commercial volumes during the upcoming years. And here we have a joint venture with the Swedish refinery Preem, and we have long-term collaboration with the forest industry as well. And on the other hand, we also have another focus area at RenFuel, which is within bioplastics. And this is a slightly younger area of development, but we have two trademarked innovations called Lignisol and Ligniset. And currently we are in a proof of technology verification stage within this area. And I'm going to give a bit more of a detail about our materials shortly, because this is actually the area that we chose to introduce into Mistra SafeChem program. But first, I'm just going to show you the value chains for RenFuel. So as you can see in this slide, regardless of if we are within the biofuels area or the bioplastics area at RenFuel, we're actually approximately at the same place in the value chain, meaning that we connect the forest industry with another industry, essentially by taking the raw material from the forest industry, turning it into a more valuable product that can be used in another industry. So for biofuels, this is within the refinery industry, and for bioplastics, this is within the plastics industry. But with that said, I also have a slide here where I have presented a bit more details about what we call the Renfuel materials area at Renfuel. And what you can see here is a slide showing some information about our two lignin-based polymers that we use as a bio-based plastic substitute. So to your left, you can see lignisol, which is a thermoplastic polymer. And lignisol is almost like the Renfuel materials answer to a lignol. As you remember, the lignol is the drop-in biofuel. Lignisol is like almost like a drop-in plastic. So this is blendable with other plastics, and it's intended for use in processes such as extrusion and injection molding. And here we look at packaging as the primary focus area. And on the other part of the slide, we have a thermoset polymer instead that we call ligniset. So this is a curing polymer, and the fact that it is a cross-linking compound makes results in the fact that you cannot blend it with other plastics. So we use this one on its own. It gets stronger than lignisol itself, but we can also make it quite flexible, as you can see in the most right picture here, that you have almost like a rubbery material of ligniset. So one intended use for ligniset is as a resin in composite materials, where we combine ligniset with fibers for composite application within, for example, the construction industry and the automotive industry. But what I want you to remember from this slide is lignisol, the thermoplastic polymer, because that's the one that we have introduced into a case study within Mr. SafeChem. So one task that we've had throughout the last year within Mr. SafeChem is actually that we had the opportunity to join a life cycle assessment course at DTU. And this was an opportunity provided to us by Peter Fanke, which we are very thankful for. And the aim of this study was to introduce lignisol, and we wanted to determine if plastic products based on a lignisol blend has a higher or lower environmental impact compared to other plastic products. So when we drafted this case with the student group, we chose to have a lignisol blend made out of lignisol plus PLA as the corresponding polymer here. And the reason for choosing PLA was that it is bio-based and it is biodegradable. So we wanted to have that as a property for the lignisol blend. And we chose to compare the blend with bio-based polyethylene and fossil-based polyethylene. So one thing that should be noted in this type of study is that we are in a proof of technology, meaning that this type of study means that we have to make some assumptions and approximations within the case scope. However, what we wanted to get from this study was to get an indication of relevant points of low impact score, but also potential focus areas that we need to consider for further development. So this is like an initial screening, which was excellent for this type of student work, I believe. And I would like to say that even though it's a student work, it's not a formally reviewed LCA, I would say that the quality of the work was extremely well done. And I'm not going to go into detail on presenting like the entire LCA study because I obviously don't have time for that, but I have inserted a brief table that is taken right from the final report in this slide. So you can see that here at the bottom of the slide in table 2, where 3 damage categories have been listed. And these damage categories are compared in different units that you can see. I will not go into detail about what the units mean, but what I want you to know is that these are common metrics used for measuring environmental impact with respect to each of the damage categories. And in this table, you can also see the different polymers that we compared, and these are color-coded. The color blue means that it had the lowest impact in that category, so basically the best performance. The red one is the highest impact, so the worst performance, and the white means somewhere in between. So what you can see here is that the Lignisol blend was performing quite well, especially with regards to the resources damage category. But we learned quite a lot from this study as well. And one thing that we realized is that the approximations that we make have a potential big impact on the final result of the LCA. So already now we have identified points that we should reconsider for future approximations and iterations on the LCA perspective. And two examples of these are the energy usage at the pulp mill that was approximated and not necessarily comparable with a realistic case for our lignin-based blends. And then we also had the matrix polymer, obviously, PLA, that had a high impact on the total score. And this is model polymer. The Lignisol itself is, of course, the polymer that is most in focus here. So in the final products, maybe we're using another matrix polymer. So this is also a part that we might reconsider and will think about moving on from here as well. But these results are quite interesting, I would say, and it also gives us an opportunity to actually keep working in this area in Mistra SafeChem. So what we will do from here is actually that we're currently drafting a case study on human and ecotoxicology for Lignisol, and this is with the great help of Anna-Karin Hellström at RISE, who is also involved in Mistra SafeChem. And the input data for this study will be partly derived from the DTU study itself. So what we want to look at here is basically the impact from choosing different areas in formulation for early stage screening. So, for example, what would the impact from the choice of lignin be in the recipe formulation? And to give you a brief background here, we can actually use different types of lignin when we create our materials. And these lignin types may differ based on the isolation type. So that's something that we're quite interested in looking at even further. But this is a case study that is in a very early drafting stage. So maybe next time when I speak, I might be able to tell you a bit more about the overall scope of the case study and maybe initial results. But with that said, I think my time is running out. So I would like to thank you so much for listening. If you have any questions that might arise after this webinar, feel free to reach out to me. I have my contact information here. And thank you so much, Mr. SafeChem, for having RenFuel as an industry partner in the program. We find it very valuable to be here. Thank you.
Clara, thank you for a nice speech, and your voice made it despite COVID. Great, and it's nice to see how the program can help you evaluate your processes and materials and bring them to get better knowledge about their potential impact. It's happy to see that. Next is Adam Slabon, assistant professor at the Department of Materials and Environmental Chemistry at Stock University, who will tell us about how to address chemistry in green. Right, Adam?
Yeah, thank you, Richard. Can you hear me well? Is it okay? Can you hear me?
Yeah, okay. Very well.
Good. So, hi and welcome to my talk. I want to tell you today why it actually pays off to make green chemistry. And before I start with, I would have a comparison. Let's see the performance of nature and the chemist and see who's maybe better and who should learn from who. And I think a common category would be the production of polymers, which we also have been talking today a bit. Now, nature has around 1.5 trillion tons of trees, and these are biopolymers on Earth, and we are making per year in the chemical industry around 350 million tons of plastics. So you see, in terms of polymer production, nature is by far much more advanced than we are here. And if we look at the raw materials, nature is using CO2 directly from air. So it does photosynthesis very efficiently. And we, the chemists, we are using in the industry crude oil, and we are actually emitting CO2 as our waste product. So nature is also emitting CO2 as waste product, but it has a recycling mechanism. And with CO2, it contributes to global warming, as you can see on this map in CO2 levels. So we cannot make more efficient chemicals than nature. We cannot use more efficient raw materials, apparently. And to put it like in another picture, how does nature do polymer production? First, it splits water into hydrogen and oxygen with solar energy. Then the CO2 kicks in, and that's how nature is building up its polymers. So within this, you can see that we have a good chance to learn from a great chemist, which is nature, and to make our materials better. And in Mr. SafeChem, we are working on this. And in particular, we are thinking how we can reduce risks stemming from nanoparticles using also nature's biodegradation mechanisms. I will give you here an example in terms of lubricants and additives for motor oils. You may know that if you have all types of engines, you need lubrication. And for this, you need motor oils to get efficient lubrication here. This accounts for cars and also for machines in industry, so you cannot get without it, actually. And we have, in also the cases, additives like the so-called ZDDP molecule, which is widely used in lubricants. And if you think about this chemical, it doesn't look so safe, and I will show you it's actually not. But what's happening here in motor oils, you're giving this as an additive, and then it's believed that this chemical decomposes in situ. It makes a tribofilm on the surface, and it protects the surfaces and enables efficient lubrication. But if you think about green chemistry, you have to think about the full life cycle. So what's happening at the end of the performance of the product? And that's where we came in, because it was believed that these kind of, let's say, polymeric films, they decompose into safe end products in carbon soot particles. So this is a carbon soot particle which you get from motor oils at the end of the life cycle. You maybe know it from when you change the motor oil of your car. But what we found with a new developed method using electron microscopy, that actually something else is happening, and we have here a potential hazard. So this kind of polymeric films, they decompose after the end of the usage into such particles of, so you have carbon soot particles, and inside you have much smaller particles of zinc oxide doped with phosphor and sulfur. And this is a potential hazard, actually. So you see, when you think about green chemistry, you cannot stop only at the performance. You have to think about the effect on the environment. And that's the point we are targeting with Mr. SafeChem. So we are thinking how we can prevent such nanoparticle hazards to occur. And another application of this is actually catalysis. So we are also thinking where you can maybe substitute particles with greener materials. And that's where actually the carbon materials come in. So we can learn from nature how to maybe make more materials benign by design. And I will give you here one example. We have shown that you can use such a carbon catalyst doped with nitrogen in different positions, like pyridinic and pyrrolic, and it's also an efficient catalyst. And if you think about catalysis, why is this actually important to have such a material? And we have shown it for the oxidative dehydrogenation reaction. And this is quite interesting from the green chemist's perspective, because if you think about plastics like polystyrene, you're using crude oil, as I have shown you. But what if we take from wood, we separate cellulose, we then go to sugars. Oh, sorry. From sugars, you can go to furanes, you can then get ethyl benzene. And if you then dehydrogenate the ethyl benzene, you can get to styrene, green styrene, and after polymerization, you have green polystyrene made out of trees, actually. And this catalyst, it doesn't have any nanoparticles inside, and it's quite efficient for this reaction. Basically, you have, first of all, no leaching of nanoparticles because you have a benign material. And if you introduce the nitrogen here, you can increase the catalytic activity for this dehydrogenation reaction by 30%. So I believe that in the future, we have to work hand in hand with nature, and Jan Erling Beckwald has shown this in his presentation very nicely, where he was merging two directions, like catalysis and biomass on the cellulose-supported catalysts. So for the future, we think that we have to work on a company like Ligninorg, which combines lignin or other biomasses with inorganic materials, because nature has given to us already the best biomass or the best polymers like lignin, cellulose and hemicellulose, and it's our role to make better materials out of it. And Clara also mentioned the lignin. And I believe in terms of lubrication that biomass will play a crucial role into the future. Because if you think about the lignin, 25% of global energy consumption is friction phenomena related to. So if you want to save energy, you have to get efficient lubrication, but also think about the end of the life cycle. And in our opinion, also within SafeChem, that's where the lignin comes in. Only 2% of lignin are being used this year, or in total, for applications without burning. So most of the lignin, you just burn it. And our approach is that we can kind of cut this lignin into smaller molecules, functionalized molecules, and use them for lubrication applications. So you want to get the same performance as existing industrial solutions, but just to have a more green design here. And I will show you how we are approaching this in SafeChem in the future. So we want to use lignin to replace such nanoparticles in lubrication applications. So if you think about the market of bio-based coatings, today we have only 5% of coatings based on bio-based materials. And we envision the future that we can increase the share to, let's say, a much higher extent here, if you think about the market. So this tends towards a bio-based lubrication design without nanoparticles or green nanoparticles. And how do we do this? As I said, the lignin is quite interesting. And I will show you on a model compound, this one here. This is a model compound for lignin because it has a similar linkage, which we want to break here. So what we are doing is we take this molecule and we electrochemically cut it into smaller parts. So in practice, here's a reactor. You have a copper electrode, a reference electrode, a counter electrode, and you can dissolve this molecule in a green solvent, and then you can apply a current, and with electricity you can cut this molecule into different parts. You can also change the reactor type and also change the selectivity of this reaction if you make a membrane here in between the reactions. So you separate the reduction reaction from the oxidation reaction. And depending on the type, we can make this model compound different selectivity, and we can tune and affect the outcome of molecules we get in the end. So here's a list. Don't look so much into the details, just remember we can control the functionality of the molecules by applying the right catalyst and the right current here. And that's what we aim to do in the future. This is just the model compound, which we dissolve in a so-called deep eutectic solvent, ethylene glycol, choline chloride. It's a green solvent. But in the future, within SafeChem, we will go towards real lignin depolymerization, which we are doing already now. And we will use levulinic acid as a solvent. Why this? Well, if you have cellulose, you can get waste of cellulose, like old paper, and you can convert it to dissolve the lignin. So in other words, you can say we are dissolving somehow wood with wood. And if we do this approach here, we believe that we can get efficient lubricants, additives, and also protective coatings on different surfaces. So that's our task in SafeChem, and what's important to note, for this you need also the life cycle analysis and also the assessment of the toxicity. And we are very happy and glad that we can work together with Work Package 3 and 5, who can have this expertise, and we can work hand in hand to get a complete picture of our chemistry here. Towards the end, I have one more example, which I wanted to show you today. So Jan Erling has talked about the cellulose-supported catalyst. Clara has talked about lignin for new materials platforms. I will show you one more example and come back to the question with the nanoparticles. So can we always prevent nanoparticles from being necessary? Actually not. We need both things. We need the design where we have nanoparticles for specific applications, but also maybe some green substitutes so we can replace nanoparticles. And one example here I want to show you, it's also the last example. For the future, for a green economy, can we make base chemicals out of water and air? So this is very often referred to as the air economy, where we make chemicals out of air. And I will show you one example. It's the production of hydrogen peroxide from seawater. Why this? This chemical is very important and the market is growing. And to get today hydrogen peroxide, you need the so-called anthraquinone method. So this means you have to use this molecule to get hydrogen peroxide, but you always need hydrogen to close the cycle here. And the question is, where do we get the hydrogen from? Of course, for example, methane or some other sources. So this also connects to CO2 emissions. So would it not be fantastic if you can just, for example, make hydrogen peroxide out of seawater? So imagine you go to a beach, you take a catalyst, you throw it into the sea, and it starts producing with solar energy hydrogen peroxide. So can this work? And again, I think we have to think about green chemistry we design and make bioinorganic materials. So this is our idea. We want to get on a lignin-supported catalyst, hydrogen peroxide. And for this, we need actually, in this case, we need particles, like this bismuth oxygen bromide, 111 system. You can see such nanosheets, and we are growing them directly on lignin. Here you can see the catalyst with lignin as support. And what we get is quite amazing, because only with the lignin as support for these nanosheets, we can get the best performance. Here's a graph. You see the produced concentration of hydrogen peroxide from seawater. It's in micromoles. The scale is like this 3000 because the standard is usually in micromoles. And here's the time. So here's the generated amount of product. And you see, if you take a look at BOB, that's the pure inorganic catalyst with bismuth oxygen bromide. So you see, it kind of stops at a certain point, but if you grow it on lignin directly, you get the best performance actually. So it pays off to make green chemistry. That's what I want to say here, because you get the best performance and also work with nature's biodegradation mechanisms. So to sum up, I hope I could convince you that in the future, there is no competition between nature and chemists. We have to work hand in hand together. Like this koala, this is us, the chemist, this is nature, and together we can make better materials with an intrinsic biodegradation mechanisms. And we have to implement, as I mentioned, the recycling technologies of nature. With this, I would like to thank SafeChem and the companies and partners from academia involved. And I believe that in the future, we can be very successful together in our collaboration. With this, I would like to thank you, and I give a word back to Richard.
Now that concludes the three speakers, and we have time for some questions. So if you have questions or comments, please write in the chat. Have some here, which I'll bring up. The first one goes to Jan Erling. And it is, could you reduce the chloride in the CNF with sodium borohydride instead of using silver?
Okay, I see what you mean. To have a reducing agents removing the chloride, we haven't. I don't think it works so efficiently as the silver, and we haven't tried specifically to use the reducing agent to do that, because we are reducing at some point. So if that worked, we would have seen it. So I don't think it works very well.
Okay, thank you. And a question to Clara. So it's about the lignin. Pulp mills today burn lignin. What would replace the energy needed?
When it comes to smaller amount of lignin, so for example, looking at lignin-based materials, you don't actually disturb the energy balance by taking out smaller amounts. So in the very early case, we don't have to consider the energy balance disruption when taking out lignin from the pulp mill. And other than that, there are solutions that can be considered. So for example, maybe we could burn the bark instead to provide the energy needed to restore energy balance if we were to take out all lignin from the pulp mill.
Okay, thank you. And another question to Clara. Do you know anything about recyclability of the plastic blended with the lignosol and the bioplastic?
Yeah, absolutely. Very nice question. So when it comes to end of life, this is obviously something that we need to consider all the time when developing and designing our materials. So the short answer to this question is yes, recyclability is an option for lignosol, but it also has to do with the plastic matrix, obviously, that we're looking at. So if we combine it with something that is not biodegradable, maybe this is not an option. Sorry, my brain is not with me entirely. So recyclability is absolutely an option, but another aspect that I wanted to mention is the biodegradability. So that's where I'm mixed up. When it comes to the biodegradability, we believe that this could also be an option for end of life, because lignin itself is actually a polymer that is generally accepted as a biodegradable polymer. However, this might be an option depending on the application that we're looking at, and we're currently evaluating under which exact conditions our lignin-based materials are biodegradable.
Thank you. A question to Adam. Any ideas of why the lignin support makes the process more efficient?
So we believe there are three aspects here. Number one, you are changing a bit the reduction potential of a catalyst, so it's becoming a bit higher. So the reduction power of a bismuth oxide bromide is much higher if you have a lignin support when you grow it there. The second point is you improve charge carrier separation, so you have a kind of electron sink with the lignin. So you can, because for the reaction, you need to separate the holes and the electrons. And if you do it on lignin, you have higher separation. That's what we can measure. And the third one is we also think that the lignin is an active support here in that case to facilitate kind of the reaction environment. So these are the three reasons for this, we believe right now. Yes. I would just mention it's the first example where the lignin works such good as a support for such a reaction. Thank you for the question.
And you, Adam, had a question for Jan Erling.
Yes, actually two. So Jeb, my first question, the XPS spectrum which you showed of palladium, this binding energy, was it palladium 0 or was it palladium 2+? Because I didn't.
Okay, this XPS spectrum contain both actually, but they are not separated. So you have to do that. I mean, by theoretical treatment, and we did that also so we can see the components. In the case where palladium 2 predominates, there is about, I think, 80 to 90% palladium 2 and 10 to 20% palladium 0. When we have palladium 0, it's the reverse. It's close to 90% palladium 0 and 10% palladium 2. So the picture I showed you were not separated. So it's the two peaks of palladium actually.
Okay, good. Thank you. One more question, if I may, Jeb. The coordination environment of your palladium on the APTES immobilized particles, you showed that it's binding to the amine groups here. But how is the coordination environment? Do you have like two amines binding to the palladium, or how can I imagine this?
Well, it's hard to tell from the data if you coordinate several or if you coordinate one, but we believe that you coordinate two amino groups when you have the palladium 2 before reduction. After the reduction, it's really hard to tell.
Okay, thank you.
Thank you for the questions and for answering the questions, and thanks for presentations as well. Before I let you in the audience and the speakers go, I just would like to make you aware of the previous seminars that we had on green and sustainable chemistry, and also on risk and hazard prediction. And these can be seen from our, if you go to our webpage, you can access these and watch them now. And upcoming webinars are also coming, and that's in March. If the next slide, please. And that's on life cycle assessment and management. So you can register for this one and you get an update of the progress of research in this field and also related to this program. And with that, it's 9:15. I thank the speakers, the people that made the questions, those of you working with the technique, and all of you listening. And I hope you have a nice day today. Goodbye.